Hi, this is David Bonacturtle. Welcome to video 5D, which is the fourth of 5 videos devoted to the 2012 Financial Risk Manager topic of market risk measurement and management. I published this on March 13th, and you can download it subsequently. So as we continue in sequence of the study guide, that means we have several chapters from Kevin Dowd's textbook, Measuring Market Risk, 2nd edition. I actually recommended a couple of these chapters to GARP years ago, and we still have Kevin Dowd in the curriculum. So I think it's an excellent textbook. He is a mathematician, and so he does sort of assume some math if you have any time at all. Chapters 1 and 2, which are not assigned, are absolutely helpful as some of the basic foundation. So let's go ahead and take a look, get started, although briefly I do have some learning spreadsheets as usual associated with these readings. 5D 1, 2, and 3, which are expected shortfall, Gaussian cupola, and illustrations of the extreme value theory examples. And then again this year, I've decided not to tag any of them as highly relevant, just from an exam perspective. So as you probably know, that means that you won't be missing anything to not look at the spreadsheets. If you're interested in a more concrete understanding, I might save that for later if time is short. So Chapter 3, Estimating Market Risk Measures, we start with estimate VAR using a historical simulation approach. And then an example that I think I've selected straight out of the Dowd. So the historical simulation to VAR in some ways is the simplest of all. Now we don't have the full data set here, but what we have here is an assumption of 200 daily profit and loss data points. So you can see some are profits and some are losses. Says on a certain day there was a daily profit of 1,946, and then the next day there was a loss of 2,524. The units don't particularly matter here. So in historical simulation, as opposed to parametric, we have a bunch of data. We do not have a distribution. And in this case, it's I like to call messy data because it's just an unsorted list of profits and losses. And then notice the portfolio of 200 profit and loss observations then gets sorted or ordered. So now it's not when it happened, but here we have the highest profit was almost 6,000, all the way down to the greatest loss, negative 3,039 for the loss. And so once sorted, the simple historical simulation is very straightforward. In this case, when we have 200 observations, what's the 95% value at risk? Okay, so I'm going to acknowledge right away that we have some discrepancy in the authors between Dowd that we're looking at and, for example, Jorian in the handbook. But I'm going to stick with the assignment Dowd. 1, because it's assigned. 2, because I also think it's a little bit more elegant and consistent. So I'm using the Dowd. It is assigned, and I'll acknowledge that Jorian here would show 10th worst and 2nd worst. Okay, I can't do anything about that discrepancy. But if we say 200 observations and the 95% VAR, what that means then is we have 5% significance and 5% in the tail. So 5% of the 200 observations is 10. So that means we have 10 of the worst losses in the tail, can't show all of those, and we're going to draw the line at the 95% VAR as the 11th worst loss. So you can see here's the worst loss, 2nd, 3rd, 4th, 5th, 6th. We would count up there in this. I'm not showing those. We would get to the 11th, because at the 11th worst loss, then we have 10 observations that are worse than that. So 10 observations that would be in the tail. Okay, so it's maybe easier to see the 99% VAR here. At the 99% VAR corresponding to 1% significance, you'll recall VAR is always one-tailed. 1% of 200 is 2 observations. So what we mean is after we sorted them, that means that this loss observation here and this loss observation here are both in the tail. The 2 of them constitute 1% of the overall observation, And so we're going to say that the VAR is right here at the third worst loss. And I like that also because that says that's consistent with our phrasing of VAR, where we emphasize the significance, not the confidence. So in other words, this 99% VAR is this number, and then we could say it as follows. 1% of the time, we expect the loss to exceed this VAR, to be down here. Then we have estimate the VAR using a parametric estimation approach that assumes that the return distribution is either normal. Okay, and so then we have what should be the familiar parametric normal VAR, could call this delta normal VAR. And then I will also say that despite the next slide, this is the one you should prepare for and expect. This is the one that 9 times out of 10 GARP's going to query on. Right, and this is Dowd's notation as well. I'm always consistent with the assigned notation. That means sometimes it's a little different than the notation we see elsewhere. And then I don't have this time scale. This is reduced to its ultimate simple. And so we can assume these are annual or per annum statistics. And we can see here with a mean or drift of 10% per year, or expected return of 10%, and a standard deviation of 20% or per annum. Then given a confidence level of 95%, you'll recall that if we assume normality, the 95% confidence corresponds to a one-tailed deviate of 1.645. Should have that memorized. And then as of part 2, really, that should be secondhand nature. And then we can then compute this parametric VAR using a normal distribution, negative the mean or drift, negative 0.1, plus the standard deviation of 20% or volatility multiplied by the deviate, and see that small z connotes a standard normal deviate given some confidence or significance level. I'm going to say confidence or significance level there just because there's sometimes ambiguity. I read that as significance level, so I read that as 5% significance, although I think Dowd may use that as the confidence level, but I don't think that's critical as long as we know what to which we refer. And then you can see that if we multiply that, we're going to get a 95% 95% VAR of 22.9% in percentage terms. So we could also wrap this whole thing in parens and multiply by the current value of the portfolio. We'll also note that by including the drift term, we have specified here an absolute value at risk, right? An absolute VAR. If we did not include this, it would still be okay. It would just be called a relative VAR. So put another way, the relative VAR is the absolute VAR if the drift is omitted, or if we assume the drift is equal to 0, which we oftentimes do when the period is daily. So sometimes daily it doesn't matter. Now Dowd also shows a similar expression under the log normal parametric. So you can see this formula here. 1 minus the exponential, and then we have the exponent here. Actually very similar terms. I mean, you can see a similar syntax here. But now the VAR is going to be slightly different at 20.46%. So then technically this would be the log normal VAR, which Dowd likes to use. But again, we don't really see that in the FRM outside of the Dowd assignments. So then with the expected shortfall, or we could sometimes call the conditional tail expected loss. This is an improvement in VAR in a sense because it gives us some information about the tail. And so now what we're doing is we're saying what is the average loss conditional on the loss exceeding the VAR. And so in a historical simulation, it's similarly fairly straightforward in the sense that wherever we draw the VAR line, there's a set of losses in excess of the VAR, and then we take the average of those excesses, right? It's the average of the loss conditional on the loss exceeding the VAR. Okay, so visually that's still a little too abstract. What I did is I pulled forward a question from GARP's 2011 practice exam. So GARP just published this last year in the practice and was the first question on their Part 2 exam. So I thought that was interesting. GARP does like to query the expected shortfall. Part of the reason is it's popular as an improvement, or I probably should say, as a supplement to VAR. Okay, so let's look at the question that GARP used. After estimating the 99% one-day VAR of a bank's portfolio to be $1,484 using historical simulation with 1,000 of the past trading days, you are concerned that the VAR measure is not providing enough information about tail losses. You decide to re-examine the simulation results and sort the simulated daily P&L from worst to best, giving the following, which gives the following worst 15 scenarios. So that's part of the question, is the exhibit here. So the question, so we had daily profit and loss, and then obviously been sorted from worst to best. So what we have here are the worst 15 out of 1,000. And then also note GARP's tilting an important piece of information here about the weakness of VAR, commonly tested, right? That VAR here of 1,484, if that's our VAR, it just says that 1% of the time, 1% of the days, we expect the loss to exceed that. But it gives us no information about the shape of that tail beyond the VAR. So that's the weakness of the VAR. That expected shortfall supplements, and so there's a point of the exercise. So what's the 99% one-day expected shortfall of the portfolio? Well, then the answer, and what you need to do for this, is identify the worst 10 observations, because it's 10 out of 1,000, that's 1%. The 99% confidence corresponds to 1% significance. And so here is that 99% VAR, and right away let's acknowledge this would not be inconsistent with Dowd's definition, right? Dowd would get the 1,450 as the 99% VAR. So see how we just have to be flexible to that. GARP has used Jorian's definition here with the 99% VAR. We just looked at Dowd, and we're assigned Dowd that would give this value here. So we have to stay flexible. The question is said to assume 1,484 VAR. However, we don't need it for the expected shortfall, because it's going to be the average loss conditional on exceeding the VAR, and so it's the average of the 1%, the worst 1%. So hopefully you can see my orange shading. I shaded the worst 1%, that's 10 out of 1,000. So you'd know that seeing the 99%, you'd know that corresponds to 1% significance. You'd multiply 1% times 1,000, you'd get 10. And you'd know that expected shortfall needs to be the average of those values. And let me say it probabilistically again. Why are we averaging these values? Because we want the expected loss conditional on the loss exceeding the VAR. So it's got to be the average of the values in the tail. And so we just add those up, divide by 10, and we should get 1,945, and that's the answer to the question. So there's some concept that goes into it, but in terms of getting the answer, all we do is average the worst 10. Dowd asks us to define a coherent risk measure, and so this comes up a lot, and the simple reason is that, let's cut right to the headline. VAR is not technically a coherent risk measure. However, expected shortfall that we just looked at is a coherent risk measure. And so the basic idea is that coherent risk measures are superior in some senses, and VAR has a weakness for not being coherent. And that's because coherence here technically requires meeting all four of these conditions: subadditivity, monotonicity, positive homogeneity, and translation invariance. Monotonicity means that a random cash flow or future value y that is always greater than x should have a lower risk So this means that less needs to be added to the y than to the x to make it acceptable. Positive homogeneity implies that the risk of a position is proportional to its scale or size. And so Dowd says this one makes intuitive sense if we are dealing with a liquid position in marketable instruments. So my quote example here is double the portfolio, we double the risk. That's leverage. And translation invariance requires that the addition of a sure amount, that's C the constant, requires pari passu the cash needed, reduces pari passu the cash needed to make our position acceptable. So those three, frankly, are bordering on esoteric, and the reason subadditivity is highlighted is that this is the one that matters. VAR technically violates subadditivity, and that means VAR technically is not coherent. Subadditivity says that the portfolio's risk should not be greater than the sum of its parts. Hopefully that's intuitive. If we had a position here and add it to another position, the risk of the portfolio should not be worse than the sum of the individual risks. And typically, you might look at this and say, well, no, VAR is subadditive, because the examples we look at where we assume a normal distribution, because normal is an elliptical distribution in the elliptical class, those will qualify. So when we're dealing with in that mean variance framework, we're not going to violate subadditivity in the sense that you've seen that before. When we take an individual VAR and add it to another individual VAR, the worst we can do is a perfect correlation where the sum of the individuals equals the two asset portfolio VAR. But we're not going to be able to add an individual VAR to another individual VAR and get a diversified portfolio VAR that exceeds the undiversified portfolio VAR. So we're going to be okay as long as we're in a normal as a subclass of elliptical distribution. However, though, it's not difficult to show some violation if we leave that distribution. So VAR is not going to be subadditive. Technically, VAR is not coherent. That questions come up often in the GARP as a quiz of this section. Next, we're asked to describe the method of estimating coherent risk measures by estimating quantiles. And so here, the spectral measure, Dowd chose a method to estimate the coherent risk measure. The spectral measure is coherent by here assuming a gamma and then some sort of a weighting function. And now Dowd shows the math of the weighting function, but I'm not going to go into it here. It's in the spreadsheet upon which this is based. But suffice it to say here that there exists some weighting function, and you can see here greater weights are applied to higher confidence levels. So if we can use a parameter and then produce the weighting function, all he's done here is for each of the associated confidence levels, say 90%, here's the normal deviate, multiplied it by a weight, and then added these up. These are in this display rounded to 2 decimals. They go out further. But if you take them out further, there's not a rounding error, and we sum the risk measure. We sum these products, and we get a risk measure which estimates the coherent risk measure by estimating the quantiles. Describe the method of estimating standard errors for estimators of coherent risk measures. A coherent risk measure is an L estimator. L estimators are asymptotically normal. They can be computed numerically using suitable numerical integration procedure. An alternative is to apply a bootstrap. And as a final, in this chapter, we can use the QQ plot to identify the distribution of data. So we plot the empirical quantiles against the predicted quantiles. So here, if it's a normal distribution, we would have predicted quantiles here on this axis, and empirically these would be the quantiles that we actually observe in the data, such that if the data were normally distributed, we should get roughly a 45-degree line. So the QQ plot gives us a quick visual way to assess whether this data is well fitted to the distribution specified here that manifests as these predicted quantiles. So for chapter 4, is a focus on non-parametric approaches, starting with describe the bootstrap historical simulation approach to estimating coherent risk measures. And so the idea here is we start with a data set of indexed returns. So again, think of this portfolio in 2 dimensions, right? The portfolio here goes down this column. And in this example, the portfolio consists of 4 assets. So that's the column vector. That's a column vector of positions in assets. Together constitutes the portfolio. And then over time, we're going to have returns, right? So we've got time as the dimension in this row, and the portfolio represented as a vector of assets in the column. The returns are what they are, and then we can index those returns off some baseline, and we have the matrix of returns. So in the bootstrap historical simulation, we're drawing random samples, but what we're doing is we're going back into the history and picking out a column vector. So maybe we simulate for the first day, we go back and use a random function to randomize and pick one of our column vectors. So for example, we pull from March 6th, the column vector, and our random sample determines which day we draw from. Having determined that, then we go pull the actual index returns for that day. So notice that's a column vector of index returns that actually happened on that historical day. And then we're saying, okay, we're going to assume or simulate that that's what happens today or tomorrow. And then that'll give us simulated prices. And then we go forward another day. Notice how it's looking like a Monte Carlo simulation. So it is a simulation. But when we go forward the next day, it's not based on some kind of engine like a geometric Brownian motion. Rather, to find out what it does from today to tomorrow, we go back, draw from our sample with replacement, random draw with replacement, and maybe we randomize and decide to pull from March 5th, that column vector of actual index returns. And we just apply those returns. So whatever happened on March 5th, we assume that happens on n+1. So those index returns will give us new values, simulated values. And then again, we do that for n+2. For the next day's behavior, simulation, we go back and pull from an actual history. And this will allow us to simulate going forward these values of the portfolio. So let me make an important point here about the correlation. This means that when we go back with a bootstrap simulation and we look at, for example, we decide to pull from March 6th or March 7th, and again, n+1 might pull from March 6th, and then we go to n+2, it might, because we're doing we're a random draw with replacement, we might go back and use March 6th again, just by virtue of random sampling. So we can repeat. Now, when we pull that vector here, notice any of these, I like to think of this as cross-sectional correlations. To the extent asset 1, 2, 3, and 4 had any correlations within that day, those do get picked up, right, in these index returns. So these cross-correlations, or what would just be called correlations, do get preserved or do get incorporated into our historical simulation model. However, what does not get incorporated, you'll notice, is when we go forward each day. Historically, 3.5 led to 3.6 led to 3.7. We would call that auto or serial correlation. Auto or serial correlation would be correlation across time. And now, if these assets were auto correlated, notice because we're going back and randomly selecting each day, maybe even with repeats, the auto correlation is not being picked up in the historical simulation. So the summary point there is, this has the advantage of picking up these, what I would call cross-sectional correlations, or just correlations. Those do get incorporated in the model. However, it would not pick up autocorrelation or correlation across time. Describe historical simulation using non-parametric density estimation. Simple historical simulation only allows the VAR estimate at discrete confidence levels. Non-parametric density estimation treats data as if they were drawings from some unspecified or unknown empirical distribution function. A simple way to do this is to draw in straight lines connecting the midpoint to the top of each histogram bar. Although better in theory, this does not necessarily produce a much better estimate in practice. So then we have some, Dowd reviews some variations on that historical simulation approach, or the simple historical simulation approach. Because the simple historical simulation approach, that's where we looked at an actual, even that GARP sample exam. We take the historical data and just sort it by the profit and loss, worst to best. each day. So if you think about it, that is an unweighted or equally weighted. We're treating each return with an equal weight. We can call it equally weighted or unweighted. It reminds me of in volatility, where we have the basic volatility is implicitly unweighted or equally weighted. And then we improve on that by GARCH or exponentially weighted moving average by weighting more recent returns. Similarly, we can improve, in theory, on the historical simulation by moving away from equally weighting each of the days or unweighting them to variations on weighting, including age weighting, volatility weighting, correlation weighting, and filtered historical simulation. So in age weighting, this is identical to Linda Allen's truncated hybrid volatility, which is a hybrid of exponentially weighted moving average and historical simulation. So the weights here are in constant proportion at lambda. And then I have an example here. If n equals 10 and lambda equals 90%, the weight in in the second period would be 90% times 10%. That's 90% times 10% divided by 1 minus 90% raised to the 10 equals 13.82%. And the ratio of these weights is in constant proportion lambda. The benefits, it's a simple historical simulation then becomes a special case where lambda equals 1 or we have zero decay. A suitable choice of lambda parameter can make the VAR estimates more responsive to large losses. This reduces the ghosting effect and is flexible to modify. In volatility weighting historical simulation, we weight the returns by relative volatility. So we have a ratio here of volatilities. It just serves as a weighting function on the return. This directly accounts for volatility changes, allows us to incorporate GARCH forecasts, can obtain VAR or expected shortfall estimates that can exceed the maximum loss in the actual data set. All right, we can see this can actually act as a multiplier, levering this up the return above 1, so we can actually get VAR estimates exceeding the actual loss. That's sort of interesting. The authors give empirical evidence to support the superiority of the volatility-weighted historical simulation. And then we can have correlation weighting. This approach is a major generalization because it gives a weighting system that takes into account correlations as well as volatilities. Filtered historical simulation, a semi-parametric bootstrap which aims to combine the benefits of historical simulation with the power and flexibility of conditional volatility models like GARCH. And then we have some summary advantages and disadvantages, that is, advantages of the historical simulation and some of its non-parametric flavors that we just looked at, like volatility adjusted. It's intuitive. It handles non-normal returns, skew or kurtosis. In theory, it handles any position type, including derivatives. Popular among risk practitioners, relatively easy to implement, no curse of dimensionality, uses readily available data, is easy to report and communicate the results, easy to generate confidence intervals, and it can be combined with parametric add-ons. So this historical simulation is not mutually exclusive with parametric approaches. And the disadvantages are, if a history is a quiet period, the VAR estimates will be too low, difficulty of handling in-sample shifts, can be dominated by extreme losses, most are subject to ghost effect, generally makes no allowance for plausible events that might occur but did not occur, and to an extent constrained by large losses in the dataset. Chapter 5, or just the appendix, is assigned to introduce copulas. And the main reason that we look at copulas is due to the drawback of correlation. So in really all of part 1 of the FRM and the econometric section and the correlation that we're used to seeing, and denoted by Greek rho, right? That's usually that's the correlation coefficient that assumes a linear relationship. So correlation is a good measure of dependence when random variables are distributed as multivariate elliptical. for example, normal. And if the risks are independent, then we have zero correlation, although it's not the converse. Zero correlation does not imply independence. But the correlation can be problematic for non-elliptical distributions. And then we know that a key issue with the correlation is that it assumes a linear relationship, and oftentimes the relationship is not linear. And so we tend to use a broader term. And notice the aim is well placed here. I'm glad that they used the terminology here. Notice it's dependence. So dependence is a broader term and generally superior, right? Because dependence includes correlation, but includes the set of nonlinear relationships as well. So dependence is the broader term. And oftentimes it's just safer and superior to say dependence, because if we say correlation, we're implying that correlation coefficient and we're applying linear relationship. So what does a cupola do? Well, if f(x) of y is a joint distribution function with continuous marginals, so here we have these marginal or unconditional distributions. So these are the normal, or I shouldn't say normal, these are the, see, f of x equals to u and f of y equal to v. These are the marginal cumulative distribution functions that we're used to dealing with. We're dealing with single variable cumulative distribution functions here, but we have two of them. The cupola function is the glue that allows us to bind these together in a cupola function and characterize a joint distribution function, f of x, y. So the cupola enables us to construct a joint distribution function from the marginals in a way that takes into account the dependence structure of our random variables. We have, Dowd looks at some simple cupolas, independence, minimum, maximum, and then we have Gaussian cupola, T-cupola, a whole long list of possible, there's really no limitation to the cupola function that we can employ. In the spreadsheet, I've got an example of a Gaussian cupola, maybe a little mislabeling that a little bit, but not to worry for our purposes in 5D2. Under an assumption of correlation equal to 0.3, so I make a correlation assumption and then produce a three-dimensional plot, really, right, of the bivariate distribution function. So more specifically or numerically, that's the cumulative. More numerically, that's the spreadsheet really simplifies. Notice there's a few tabs in the workbook, but a lot of that's just the complexity of the cupola function itself. It boils down to the output, and these vary, just a few simple cells here. We've got a y and a variable x and a variable y, and then we can input, as in yellow, 5% and 5%. Right, to produce these, so you can see the 5% applies that normal cumulative distribution function that we're used to seeing. So here in just this one row, we have an example of that univariate marginal distribution. And then for variable y separately, we have an example of that univariate marginal distribution. Then given a correlation input, the cupola function works in the background, comes back to us and produces a joint or bivariate cumulative distribution function. See, the cupola is the glue that glued together our marginals and produced for us a joint distribution function. In this case, if we think of these as probability of default, if we have one bond with a probability of default of 5% and another bond with a probability of 5% and then some correlation assumption, we end up with a joint cumulative distribution function telling us that the probability that both of them will default, or symbolically here, the joint probability that variable x will be, less than some value and the variable y will be less than some value is going to be equal to 1.22%. How does tail dependence can be investigated using cupola? Tail independence is an important issue because extreme events are often related, and models that fail to accommodate their dependence can literally lead a firm to disaster. if marginal distributions are continuous, we can define a coefficient of upper tail dependence of x and y as the limit. And then finally, Chapter 7 for parametric approaches, Dowd introduces the two approaches, the two primary approaches as part of the extreme value theory. So I think we did see some introduction to this in part 1, but it's pretty brief. And I think at this point, probably familiar with the theory. The theory is that in risk measurement and risk management, our primary concern is not the central tendency or body of the distribution, assuming it's properly characterized. It's with the catastrophes, the low frequency, high severity events. So measures of central tendency, the mean, while useful for valuation and pricing, where we want to be precise on the mean, remember Jorian's idea, valuation is about precision in the first moment. Measures of central tendency, even including dispersion to some extent, are not as useful as our ability to characterize the tail. And that's where that I think of Nassim Taleb's criticism, that school of thought that it may be beyond parameterization. Well, that's not going to stop extreme value theory from trying. So it's a branch of applied statistics. Central tendency statistics are governed by central limit theorems, but central limit theorems do not apply to the extremes. Extremes are governed by extreme value theorems. Extreme value theory uses these theorems to tell us what distributions we should fit to our extreme data and guides us in how we should estimate the parameters involved. And so we have two basic approaches here: peaks over threshold, which characterizes the GBD distribution. So in the peaks over threshold, we take the history, we do not divide it up into time, we specify a threshold here, and then we're interested in losses above the threshold. So it looks a little like expected shortfall, but it's really concerned specifically with the distribution of losses above the threshold. And so in the limit, how do we characterize just the behavior of these losses above a threshold? And that theory will show that we can use the GPD distribution to characterize these peaks over threshold. I think generally considered a more modern approach and more common approach, as opposed to, I have the GBD, or I'm sorry, GPD, generalized Pareto distribution, a formula for that. So GPD characterizes the peaks over thresholds. It has two parameters, positive scale and shape or tail. I believe it's called either shape or tail. Plus, we need to select that threshold. As opposed to the block maxima that divides the historical data set into time blocks and selects the worst loss within a time block. So we're asked to compare generalized extreme value and peaks over threshold. So the advantage of the peak over threshold over generalized extreme value is that the GEV involves an additional parameter relative to the POT. So if I just go back here, we got three parameters here: location, scale, and shape. So GEV has the location additionally. The most popular GEV approach is block maxima, but can involve some loss of useful data. Disadvantage of the peaks over threshold is it requires us to grapple with the problem of choosing that threshold. The choice of the threshold is the weak spot for peaks over threshold theory. It is inevitably arbitrary and therefore judgmental. So it involves a trade-off. We want that threshold to be sufficiently high enough that the extreme value theory works in the first place. But if it's too low, we will not have enough. But if it's too high, we will not have enough excess threshold observations from which to obtain reliable estimates. So if I just go back graphically to the point there, right, this threshold of excess losses, we want to set this high enough that the extreme value theory and the theory that in the limit we can characterize with the GPD distribution is accurate. If we set it too low, and you can imagine we pull this threshold down, at some point, we're eventually going to start to correlate or look pretty much like the body of the distribution, which defeats the whole point. So we want it high to be in the tail. But the problem is we set this higher, we have less and less data with which to fit the parameters. So that's a trade-off Dowd's referring to there. Now in 5D3, I do have concrete illustrations of both of the examples here in Dowd. That GEV, typically the most common is the block maxima there. And you notice that technically wasn't assigned in the aims, that GEV. That's the more traditional one where we slice the historical time into blocks. Although I do have the solutions here, and notice it's got 3 parameters: scale, location, and tail. 3 parameters. And then I've, in the spreadsheet, illustrated Dowd's examples, page 193, examples 7.3 and 7.4, where we've produced a value at risk under the GEV distribution. So we got the VAR here, given the inputs, and you can see some pretty high confidence levels. And then on the other hand, the one that is part of the aims, value at risk using the peaks over threshold characterized by the GPD distribution. Here's the formula. And then we can also, there's nothing to keep us from applying this to expected shortfall, right? So sometimes there's confusion here. The peaks, the extreme value theory, and that refers to both here, the peaks over threshold or the GPD or the GEV, either approach. They're both fully compatible with both VAR and expected shortfall, as shown in my spreadsheet. And that's because the GPD and the GEV, they just give us a function to use in the tail to complete the characterization of the distribution, right? So, but VAR and expected shortfall just use that information in the distribution. There's nothing incompatible with that. So Dowd is able to easily give us a formula for expected shortfall. And then in the spreadsheet, I have the generalized Pareto distribution. So that's the GBD distribution that characterizes the peaks over threshold approach. That's the one we're more interested in because it's going to be more common. It comes up in the case study, where we're characterizing the distribution of excess losses over a threshold, right? So that's the one with 2 parameters. So in the spreadsheet, I've got scale and tail, or if you like, beta and chi, only 2 parameters. Recall, this is listed as one of the advantages of peaks over threshold over the other one, which was GEV, or block maxima. One of the advantages, we only need 2 instead of the 3 that we need over there. However, that's sort of a wash because we do need to specify that arbitrary threshold. Here where I've got 2.0, Dowd tends to deal in standardized variables here, so we don't really, these are really sort of without any particular quantities or units. I'm sorry, without real units. Right, so here's that threshold that's sort of arbitrary. We want to set high enough so that the theory of the GPD distribution applies, but not too low that we're picking up all of the data and defeating the whole idea of trying to isolate on the extreme tail. So that's 2 parameters, advantage but disadvantage. This 2.0 is pretty arbitrary. Then we do need the number of losses above the threshold as a percentage of total data set. So that 4% here is that's a pretty focused look on the extreme losses confidence level. And then applying the formula that we just looked at here to compute, notice both a VAR, so that's a VAR, assuming the generalized Pareto distribution, characterizing the peaks over threshold approach. We've got a VAR, and then we've got also an expected shortfall. And we're not surprised that these values are higher. After all, this value is the average of the losses in excess of this VAR amount, so it needs to be higher. This is the average of the losses in excess of this amount because it's at a higher confidence level. And finally, explain the importance of multivariate EVT for risk management. Multivariate EVT models the tails of multivariate distributions, where the key issue is the tail-dependent structure of extreme events. Multivariate EVT is important if extreme events are not independent. Dowd says it is manifestly obvious that at least some extreme events are not independent. And that concludes 5D of the 2012 videos. I look forward to the next video, 5E, which will be the final in the series, in the sequence for topic market and risk. Thank you very much.